Hey everyone, and welcome to this Forge College Explainer. So if you were with us in the previous lesson for our Estimating and Optimizing Solana Costs module, you know we got our hands dirty with ad hoc instruction consolidation. We combined related operations, we refactored instruction orders, and we used measurement scripts to visibly drop our compute units. And honestly, it felt pretty great seeing those numbers go down. But as we make this big transition from EVM to SVM, we have to realize that managing costs is not just a one-and-done spring cleaning. Today, our goal is all about sustainability. We're taking those ad hoc isolated measurements and upgrading them into a fully automated continuous tracking pipeline.
Because, let's be real, we've all faced this incredibly frustrating question. Why do your optimizations just keep disappearing? It's a pain point every developer knows. You spend hours, maybe even days, obsessively profiling your code. You shave off those precious compute units, you deploy it, you do a little victory lap, and then boom. The very next pull request from a totally well-meaning teammate accidentally undoes every ounce of that hard work just because they tweaked a serialization layout or a reordered array. It's maddening, right? It's literally like sweeping dirt in a windstorm. But today, we're going to fix that. We are building a system that physically locks those hard-earned gains in place and actually alerts you before any regressions hit production.
All right, here is our engineering blueprint for today. First up, the costs tracking thermostat. Second, on-chain versus off-chain data. Third, the three-stage pipeline. And finally, number 4, CI gates and alerts. So let's jump right into section 1, the cost tracking thermostats. I want you to think of your cost telemetry as a continuous feedback loop. It's exactly like the thermostat in your living room. First, you have your probes. These are the thermometers measuring the current temperature, which in our world means representative transactions actively measuring compute usage. Then, you've got observability. That's the display on the wall, reporting the current and historical temperature so you can spot trends. And lastly, you have the gates. When the temperature spikes, meaning your compute units deviate way off your stabilized baseline, the gates kick in to adjust behavior or alert the team. It's an automated, self-regulating loop, and it's an absolute game changer. Moving on to section 2, on-chain versus off-chain data.
To make this thermostat work, we actually need 2 distinct categories of telemetry. First is on-chain telemetry. This is your absolute authoritative truth. It's pulled straight from transaction metadata returned by RPC endpoints, things like inner instruction traces and compute unit annotations. Basically, this tells us exactly what happened to our compute units. Off-chain telemetry, on the other hand, gives us the contextual environment. We're talking RPC latency, mempool pressure, cluster-wide fee changes, node CPU usage. Off-chain data explains why it happened. Say you spot a massive compute spike. The on-chain data shows you the size of the spike, but the off-chain data reveals whether it was just crazy cluster congestion forcing retries, or if an actual program upgrade caused the issue. You really need both to see the whole board. So, what exactly are we tracking? There are 4 canonical fields you absolutely must persist. First, compute units, and second, the Lamport fee, both pulled straight from the transaction meta. This translates your raw compute into real economic dollars and cents. Third, we have RPC P99 latency, usually grabbed from something like a Prometheus exporter. And fourth, slot time from the blockchain headers. Now, here's the secret sauce: timestamp alignment. When you extract these 4 different fields and align them perfectly by their timestamp, you unlock this amazing superpower to correlate an isolated compute spike directly with network congestion at that exact second. This alignment is the literal bedrock of any actionable dashboard. All right, let's get into section 3, the 3-stage pipeline. How do we move all that data from raw RPC endpoints into something we can actually read? We use a 3-stage pipeline. Step 1 is collection. We subscribe to a transaction stream, filter it down by our specific program ID, and systematically parse the meta to pull out those compute units and fees. Step 2 is aggregation. We ingest those parsed events into a solid time series database. Think Prometheus, InfluxDB, or honestly, even a simple PostgreSQL instance with a timestamp table works fine. Step 3 is visualization. We take those aggregate trends and plot them in a dashboard like Grafana. Just imagine taking those manual measurement scripts we wrote last time and wiring them directly into a database that feeds beautiful, real-time, 24-hour rolling percentile charts. That's the pipeline. Now, if you take away absolutely nothing else from today's explainer, please let it be this engineering principle right here. Treat on-chain telemetry as the single source of truth, period. When you're setting up your pipeline and creating your baseline cost models, you have to anchor them using high-fidelity, event-level execution data pulled directly from the blockchain. Your off-chain metrics are fantastic for context, but that on-chain metadata, that is your unshakable mathematical foundation. Don't compromise on it. To actually build and maintain this loop day-to-day, a really solid strategy is to run synthetic probes daily. You just replay typical transaction patterns on a non-production cluster to get clean, isolated baseline data. And hey, here's a fun little modern workflow tip for you. Use AI to generate your initial dashboard scaffolds and data person queries. Just feed the AI your telemetry field names, data types, and the aggregation windows you want, and let it do the heavy lifting. But, and listen to me carefully here, always validate that AI output with unit tests. Otherwise, your friendly AI might just hallucinate a missing instruction count. And next thing you know, you're chugging coffee at 2 a.m. trying to debug phantom network crashes. So use it as scaffolding, for sure, but never as finished code.
Bringing us to our final piece, Section 4, CI gates and alerts.
Let's talk about something that haunts every single developer, pager fatigue. There is literally nothing worse than getting woken up in the middle of the night because of a transient network blip. We call those noisy alerts. They trigger on a single isolated spike and completely ignore the broader network context. They drive you crazy, and eventually you just start ignoring them entirely, which is dangerous. Effective alerts, on the other hand, are configured as multi-condition triggers. They require a sustained deviation, like, say, a 20% spike in the 95th percentile of compute units that refuses to drop for 3 consecutive hours. They also correlate directly with those off-chain signals we talked about. By storing these specific alert thresholds as code right alongside your program source, you guarantee that you only get paged when there is an actual persistent regression that really needs human eyeballs on it.
And here is where we fully close the loop. We use CI acceptance criteria. This is how we physically block unbenchmarked code from destroying our hard-won optimizations. You set up your continuous integration pipeline so that the moment a pull request is opened, it automatically runs a quick synthetic probe and compares the PR's telemetry against your baseline JSON file. If the median compute deviation jumps over your acceptable tolerance, let's say 10%, the PR is blocked. Full stop, red light. It physically stops regressions in their tracks. It encodes your stabilized baselines into automated tests. So when your teammate accidentally changes that serialization layout we joked about earlier, the CI pipeline catches it instantly, blocks the merge, and hands them a direct link to the Grafana panel so they can see exactly what they broke. Which brings us to a really fascinating final thought to chew on. How do we turn these baselines into developer budgets? Once our continuous tracking pipeline is purring along, fully operational, and we're just soaking up all this pristine, perfectly correlated data day after day, what comes next? How do we take that historical data and use it to proactively guide our engineering team before they even write the first line of code for the next feature?
Well, I'm glad you asked, because that is exactly what we're going to tackle in our very next lesson. Up next is Foundations of Cost Modeling, where we'll formalize all these baseline statistics into a reproducible model, translating those compute unit baselines into clear, actionable budgets for your devs. And that wraps up today's explainer on tools and continuous cost tracking. We took you from ad hoc, manual scripts all the way to a fully automated thermostat that relentlessly guards your compute optimizations. I highly encourage you to head over to our website at forge.college to learn more about this subject, grab some starter prompts for your AI scaffolding, and dive into even more awesome Web3 development resources. Thanks so much for learning with us today, and keep optimizing.